All right, for our second lesson of chapter 13, we're going to take just a quick reminder of our number system values and which numbers fall under which classification. And then we're going to talk specifically about one of those, the rational functions, and how that works with recurring decimals. So a quick reminder, there is a chart on page 358 of your book. If you need to refer back to that, it's a good thing to take a look at. But simply, natural numbers are the most specific set of numbers. So natural numbers are the ones that include 0, and then 1, 2, 3, so on and so on. So no fractions, no decimals, no negatives, everything else. When you branch out to integers, now remember you are including all of these numbers, plus you're throwing in something else. So all of these numbers are still integers, but when you broaden out to the integer category, you now can include more numbers. And so now we take all of these numbers, plus we throw in the negatives. So now you have numbers like -2, -1, 0, 1, 2, so on and so on. So again, notice it still includes the natural number set, but it also includes now more numbers. Same thing is going to happen here with rational numbers. All of these are rational numbers, but now with the rational set, we can include more. So we're taking all of this, plus we are now throwing in fractions. Anything that can be written as a fraction is considered a rational number. So that would include decimals that end, as well as decimals, if they never end but they have a pattern to them, they're still considered rational. So just for one example, I'll do something like that. So if I had 0.5 repeating, that can be written as a fraction, and that's going to be the next part of the lesson, is to show how you can take a repeating or a recurring decimal and write it as a fraction. The real category is reserved for anything that cannot be written as a fraction. So anything that is not rational is something that cannot be written as a fraction. So popular values would be things like pi, things like the square root of non-perfect square numbers, like the square root of 3 or the square root of 5. Those are all numbers that cannot be written as a fraction, so we throw them into the real category. A couple things you need to understand with just some notation. Make sure you can respond properly to a true or false question. So something like this we would see as -2 is an element of the natural number set, true or false. Right? And we look up here that the natural number set does not include negatives, so -2 is not an element of the natural number set. The square root of 2 is an element of the not rational set. So in other words, this is saying that -2 is not a rational number. And we can see that that is true. -2 cannot be written as a fraction, so this is a true statement. That little apostrophe that you see there is like the word not. So that means it is not a part of the rational number set, which is true. So just interpreting some notation on those guys. So jumping down to the second part. So again, we talked about rational numbers are anything that can be written as a fraction. And so oftentimes when people see ongoing decimals like these, they immediately assume that they're not rational. But if there is a pattern to it, like the ones you see here, that means it can be written as a fraction. And so that's the second part of the lesson, is to show how you can take a recurring decimal and write it as a fraction. If there were no pattern to this, if it was just a sort of random set of numbers that were ongoing, then it cannot be written as a fraction. So, but these ones can. So the way we're going to approach these is with a simple system of equations. So we're actually going to write two equations and then use like an elimination process to get rid of the repetition and create our fraction. So in the first equation that we write, we want to write a simple equation where we have nothing but repetition to the right of the decimal. So to the right of the decimal, we can see that I do have 0.24 repeating. So that's going to be my first equation. In my second equation, I want to write another equation where I have nothing but 0.24 repeating to the right of the decimal. So if you look right up here, so if I were to multiply this by 100, that would bump my decimal over to right here. And again, you can see I would have nothing but 0.24 repeating to the right of the decimal, which is what we want. So I'm going to take this equation right here that I just wrote. I'm going to multiply both sides by 100. Right? And on the right side, that's going to bump my decimal over 2 places. So again, I have nothing but 0.24 repeating to the right of the decimal. Right? Because again, it essentially took what you had right here and it bumped that decimal over 2 places. So it puts the 24 on the left, and you still have nothing but 0.24 repeating to the right, which is what we have right now. And so the whole purpose of doing that is because now, if I just subtract straight down, so I got 1 minus 100 on the left, and on the right, when I subtract here, the repetition will cancel. So my 0.24 repeating minus 0.24 repeating would cancel, and I'm left with nothing but 0 minus 24, which is negative 24. So we were able to eliminate the repetition, and now if I divide both sides by negative 99, we have our fraction. And of course, if you can reduce that, it's always good to reduce, so do that whenever possible. So that's going to reduce down to 8 over 33. And if you have a calculator handy, you can test and see if your answer is right. If you go into your calculator and type in 24 divided by 99 and hit enter, you should get 0.242424 repeating. So jumping on down to example 2, again, we want to accomplish the same task. I am looking for 2 equations that have nothing but repetition to the right of the decimal. So we're going to start out by just getting an expression for x. So if you look at this one, we're going to say that x represents our 0.3, and then notice it's only the 4, 5 that is repeating, so that's how it would look. So that's what we're going to say x is equal to. However, when I go to write my 2 equations, I need only the repetition to the right of the decimal. So I need my decimal for my first equation. I need to bump my decimal over to here in order to make that happen. So I'm going to say, I'm going to multiply both sides of this times 10, which is going to bump my decimal over 1 place. And that gives me an equation where I have only the repetition to the right of the decimal. And so that's a good equation that we can use. And now I need one more equation that has nothing but repetition to the right of the decimal. So again, if you kind of go back up to where we started, I need another expression that has 4, 5 repeating to the right of the decimal. So if I go back up top here, if I bump this over 1, 2, 3 places, that's going to give me 4, 5 repeating to the right of the decimal. So if I multiply this original expression by 1,000, that's going to bump the decimal over 3 places. So I'm going to have 1,000x equals 345.45 repeating. So with those 2 light blue equations that you see, you can see that we created 2 equations where I have only repetition to the right of the decimal. So now when I go ahead and subtract those, now the repetition can cancel, and I'm left with nothing but integers, which is what we're looking for. So if I subtract straight down, I got negative 990x on the left. My repetition on the right will cancel. So I just have to do 3 minus 345. The repetition is gone. I can divide my 990 over. Of course, my negatives would cancel, so 342 over 990. And again, if you went into your calculator and typed in 342 divided by 990, you should see this original decimal that we started with. Of course, you can also reduce. Remember, your calculator can do that for you as well. So if you hit 342 divided by 990 in your calculator and hit enter, it's going to show you this. But if you then go into hit math and then fraction, and hit enter, it's going to give you the reduced version of your fraction, which is 19 over 55. And that's where we'd like to end, with a reduced fraction. So one more here, and again, if you're just doing the video for the first time, you may want to pause and give this one a try on your own. That's what we'll be doing in class, but here's how this would go. For our sake, again, I'll go through this one a little bit quicker because it's kind of more of the same. But again, I want two equations with nothing but repetition to the right of the decimal. So the first thing we're going to establish is what is x. So in this case, we're going to notice that x is 5.6 with only the 3 repeating. So for our two equations, the first one, I'm going to multiply both sides by 10, so I can put the decimal right here so that I have only repetition after the decimal. And so we're going to say 10x is equal to 56.3 repeating. And then again, I need another equation with nothing but repetition. And so if you look up here, I'm going to now bump it over 2 places so that I have a new equation, but again, I only have 0.3 repeating after the decimal. So in this case, to bump it over 2 places, I'm going to multiply this expression by 100. So that's going to bump this decimal over 2 places and put it right here. So 563.3 repeating. So again, you can see now when I go ahead and subtract straight down, my repetition will cancel out for me, which is what we're trying to accomplish. So if I do the 10 minus 100, I got my negative 90. And on the right, if we do 56 minus 563, you're going to get negative 507. And divide both sides by 90. And then this is a great stage. Go ahead and go to your calculator, do 507 divided by 90 and hit enter. That's going to confirm, first of all, that you got the right answer because you're going to see this on your screen so that you know you did it right. And then if you go and hit math fraction, it's going to reduce this guy down to its simplest form, which should be 169 over 30.